Welcome back. So in last class we have seen the frequency response curve of an amplifier and how the gain will be vary with reference to frequency and what are the reasons at very low frequencies uh, for gain fall. Similarly at the higher frequencies also gain fall will you can observe, and what are the reasons in case of higher frequency also we have seen. Now let us see the analysis of circuit, including considering the coupling capacitor, input coupling capacitor, the two input coupling capacitor effect. Okay, input coupling capacitor effect. So with the input coupling capacitor, the gain will be decreased, right? With the decreasing frequency, the gain also decreases. How the gain will be with the input coupling capacitor, that we are going to see now. So for that analysis, I am taking an example circuit of common emitter circuit, common emitter amplifier circuit. But here we have two different analyses. One is current voltage analysis and another one is time constant analysis. First of all, let us see current voltage analysis. Here, see, this is the CE amplifier with emitter resistor, including the emitter resistor, and also it shows the coupling capacitor in series with the RS, in series with the RS. In the basic circuit, before the potential divider network, you have the coupling capacitor, right? So now with this deriving the output voltage, right? So first of all, the output voltage is, deriving the gain, therefore the output voltage from the circuit is given by the drop across RC. The drop across RC is the output voltage. Okay, that is minus Gm V pi into RC. Okay, so output voltage is minus Gm V pi RC, where V pi is given as, from the circuit, it is IB into R pi. In the circuit you can observe the V pi is IB into R pi, and IB is obtained from the input current, input circuit is like this. In terms of IA, you can estimate IB is II into RB divided by RB plus RIB, where what is RB? RB is the parallel connection of R1 and R2, whereas IB is input resistance looking at the base. It is already derived in the CE amplifier, including the emitter resistor case. Okay, and the input current IA is, you can write the equation at the input side like this: Vi divided by the resistance. The resistance includes the different components like series resistance, capacitance, and input resistance Ri. Therefore Vi divided by Rsi plus 1 by Cs SCC plus Ri. Okay, that is the Ii. Now substituting all these equations in V naught, you can get the voltage gain. You can get the equation is like this. You can get the equation is like this by substituting that is V pi, then IB, then II. If you substitute all those equations, finally the voltage gain AV equal to V naught by Vi. V naught by Vi equal to minus Gm R by RC into RB by RB plus RIB into SCC divided by 1 plus S of RSI plus RI into CC. So if you take RSI plus RI as a common, the equation can be modified including the time constants like this, where tau s represents, where tau s is given as the product of resistance and capacitance. The resistance value is RSI plus RI into CC. Okay, So this is the analysis with including the coupling capacitor, and hence the corner frequency is defined as FL equal to 1 by 2 pi tau s, because it is at lower frequency range, and in terms of resistance and capacitances it is 1 by 2 pi RSI plus RI into CC. Okay, and the magnitude of the gain is given as, again that too in the decibels. In the decibels it is expressed as 20 log that gain formula base 10. Okay, so with reference to above analysis, here one problem is there. So calculate the corner frequency and maximum gain using this data. Okay, so you solve it, and if you have any doubts you can discuss later. And another analysis, what I said, is time constant analysis. Whatever previously we have seen is current voltage analysis. Now the time constant analysis. In the time constant analysis, directly you can write the time constant by observing the small signal equivalent circuit. But here the assumption is all the independent voltage sources must be equal to 0, and hence they are treated as short circuit. And now the equivalent resistance looking through the coupling capacitor CC is, that is RSI plus RI. Okay, therefore the time constant you can define as RSI plus RI into CC. Okay, so the time constant value is same in both the time constant analysis and voltage current analysis, right? Then coming to effect of output coupling capacitor. For this I am assuming common source circuit shown in figure, right? Like a common source circuit with reference to MOSFET amplifier I am taking. So this is the common source amplifier using MOS transistor, and the corresponding equivalent circuit. So if you observe clearly, the coupling capacitor is considered. The output coupling capacitor is considered, right? Here the maximum output voltage we can expect in this circuit is when the coupling capacitor is short circuit, right? You know, in the mid frequency range the coupling capacitors acts as a short circuit, and in the mid frequency range, what is the gain? Whatever the gain occur, that is the maximum. Okay, so therefore the maximum output is VO max equal to GM VGS into RD parallel RL. So in the circuit you can observe that the maximum output voltage, the maximum out possible is when the CC is short circuited case, current into the resistive network, that is RD parallel RL. That is the maximum output voltage. Okay, then at the input you can write the equation, the input loop, the equation is Vi equal to VGS plus GM RS into VGS. Okay, therefore substituting VGS, that is VGS is Vi divided by 1 plus GM RS. Substituting this VGS in the V0 equation, you can get the maximum voltage gain. The maximum voltage gain is, that is GM RD parallel RL divided by 1 plus GM into RS. Okay, so this is the maximum gain possible, maximum gain possibility. Okay, now with reference to this, the time constant is looking through the coupling capacitor CC, So while looking, the independent sources must be 0, right? Independent sources must be 0 means Vi is 0. So when Vi is 0, VGS also 0, and hence GM VGS value is 0. GM VGS means that is the current source value is 0, and that is treated as open circuit. Therefore, the effective resistance is looking through the coupling capacitor is given by Rd plus Rl, and hence the time constant is defined as tau s equal to Rt plus Rl into Cc. Therefore, the corner frequency with reference to this is defined as Fl equal to 1 by 2 pi tau s. Okay, 1 by 2 pi tau s, right? Similarly, in emitter follower case also, it is better to observe what is the effect of coupling capacitor, but that we can see in the next class, right?